All right, good afternoon, everybody. Welcome to our first ever replay of a seminar. This is the first time we've ever had enough demand and interest. The idea came up some time ago that we should revisit some greatest hits, and apparently this is it. So this is convenient for us whenever somebody cancels and can a few days before a seminar. As you may have guessed, I should back this up. I'm pretty sure the screen is already being shared. So what you see there is, I think it's about a year ago, I guess less than a year ago, March 24th. Dr. Quimby and I did this presentation, and to no one's surprise as to why, right? And so we figured we'd just replay it since we said a lot of good things and neither of us can remember what was said, because, right here. Yeah, and then I'll stop it before, probably won't pause it, maybe we'll pause it. And talk about something relevant, but we'll stop it before the questions and then give you an update as to what has happened this year. It's different from last year. And I think that's about it. That makes sense? Bart, good? Yeah, right.
Okay. Yeah, the unmute button, but yeah, sounds good.
Okay, and we apologize for that. We're trying to work on the audio. We've got video recording, audio, Zoom call, transmitting in room. Basically, all major problems of a zoo and a theme park. Okay, so, and we get to I didn't introduce myself because it's gonna happen here. Good? I think so. Okay. On roof. All right, good afternoon, everybody, or morning, as it is. My name is Scott Hamill, and I am both the host and the presenter this week, which I don't know if that's ever happened before, actually, but they said, "Can you be the host too?" And I said, "Sure." So this week's sort of late add to our semester schedule is a presentation on Roos ice dams. Originally envisioned to be also and some discussion about snow loads, but we may not get to that because as we put this together, we started realizing there's kind of a lot to talk about with just ice dams. So that might have to be another presentation. So presenting with me today, though not on the original schedule, which is my fault, is Dr. Bart Quimby. So in the way of, we didn't do introduction slides, but in the way of introductions, I am a professor of civil engineering here at UAA in the area of structures, and Dr. Quimby is my predecessor in the same job, actually. So that's kind of neat. I think this is actually the first time we've ever done a presentation together. Sure. I think so. That's kind of cool too. So historic things are happening. And I also think that, well, I might be the only one with a predecessor. all of our long-standing faculty have not been replaced. So, all right. So I'm going to start off. Here's a quick outline. We're going to talk a little bit about heat transfer. I'll try not to. I'm not a mechanical engineer. I don't have a degree, a PhD in thermodynamics. So that means that you will be able to understand what I'm saying, hopefully. And so we'll talk about that. And then Dr. Quimby will talk a little bit more about how, and I'll talk about what happens and why you get ice damming and what happens on our roofs. And then Dr. Quimby, who has a lot more experience than I do, sort of poking at these things and talking to people and living in Anchorage a lot longer than I have. We'll talk about what to do about them and some case studies. And like I said, we probably won't have time to get to my short discussion on snow loads. As a disclaimer for this presentation, I wanted to just one of the reasons that I pulled this together is because a lot of people were asking questions about it. A lot of people were talking about it. There's a lot of misinformation out there. There's not a super great website that explains it. And so I am not an expert in this area. And so hopefully I wanted there to be a venue for a conversation. So the YouTube chat is open, so feel free to ask questions and put in comments in there, or we'll try to leave some question time at the end, because really, the idea here was to kind of pull together engineers, architects, contractors, homeowners, and just sort of spread the knowledge, and also provide a recording at which people can look back on this. So, all right, so you want to add anything?
You're doing great.
All right, so there are three ways that heat transfers from one object to another: radiation, convection, and conduction. Right, and so radiation involves electromagnetic waves that transfer basically from a hot body to a cold one. If you go looking up radiation, there's a lot of talk about black body radiation. The idea being that if you have a perfect, quote, black body, that it will either absorb or emit 100% of its energy, in or out, depending on whether it's hotter or colder than its surroundings. And those, of course, don't exist in real life, but there are some substances that are close. I actually did a little bit of a giant deep dive, one of those like internet rabbit holes on this. And because what I was trying to find out is, and do some math on actually how much much radiation goes from a warm house to a cold attic. And I didn't get a good answer. What I got a lot of is if you live in a hot climate, there's a lot of radiation that comes from the sun that warms up your shingles and then permeates into your house. And there are ways you can put in reflective things to stop that radiation if you live in a hot climate. We don't live in a hot climate, and so it appears there's very little, at least easily available information about the other direction. And so for the purposes of this presentation, I'm going to generally ignore radiation. We know that it happens because if you take one of the versions of infrared of radiation is infrared. If you take an infrared picture of your house, you can see heat coming out, right? So we know radiation happens. But by and large, I think it's a minor part of the actual movement of heat from your house to your attic or to your snow. So that's number one. Convection is the transfer of heat from one object to another due to the movement of fluid, in this case, air, right? And so this actually involves the molecules moving from one place to another. Essentially, the hot object heats the air moves, and thereby the energy goes somewhere else, right? And so convection is not a huge movement of heat in the wrong direction. I don't know if I'm saying that right, but we'll talk about convection more as we go. But for the most part, the convection that we're going to talk about is convection that we're trying to move heat. And one of the ways that we can move heat, if we want to move heat, is convection. It's not a mechanism of heat loss, I guess is the best way to say it. It is, but it's more minor than number three. The big dog in the room is conduction, right? And so conduction is where heat is transferred basically from the hot end of an object to the cold end, or from one object to another by touch, right? So the idea here is that the molecules are moving fast and they actually are touching something else and they bump into the other molecules and heat up the other substance or move along from one end of an object to another. And an object's ability to conduct heat is thermal conductivity. So I'll talk a little bit about thermal conductivity, but the idea is, you have insulated materials, they prevent thermal conduction, they have low thermal conductivity. You have things like metal, which is high thermal conductivity, and it allows heat to move through it very easily, right? So, so those are the basic concepts of those three. The fourth thing basic concept, which I think is worth reviewing, which most Alaskans probably have a good idea of, is the stack effect. The idea idea with the stack effect is that essentially hot air rises, right? And so we have warm air, which is, it turns out that warm air has a lower density than cold air. And so, just like a balloon underwater, it's going to move upward, right? And so warm air is buoyant, and so it will move upward. And in our houses, that has the effect that, if you have a point source like a chimney or a fireplace, then that heats up the air, then that buoyant air moves upward out the chimney. It can't go anywhere else, right, because it's in a chimney. But that creates a low pressure area around the warm air, which causes suction. And so then all that air has to come in from outside. It comes through cracks, it comes through doors, it comes through windows, but it's going to generally come in near the bottom of the house and work its way up. The stack effect is most pronounced in chimneys and vents, but it also happens just in the house itself, right? Because the house is warm and the attic is potentially cold, and so air is going to move upward. So, so that's an important concept with some of the stuff that we're going to talk about. Okay, so some more conduction, going back to conduction, right? The third and most prominent movement of heat out of our houses. So as I mentioned, there's thermal conductivity, which is expressed oftentimes in U is conduction or K. Sometimes the thermal conductivity of an object is small k. But you'll see it if you start looking into housing and things related to housing. Sometimes it's given as the variable U, and that in SI units is watts per meter Kelvin. I actually get a little bit annoyed with U. Some people use U. It is essentially, if you move down further, the inverse of the R. We're all familiar, or potentially, you've heard of R value, right? Most construction materials are rated in terms of their R value. So those are just inverse of each other. So if you see U, you just inverse it and you have the R. Essentially, one is how much, U is how much heat will pass through, and R is how much you're stopping heat, right? A higher R value is less conduction of heat. So better insulator. A higher U value means better conductor of heat. So I'm going to stick with R value for the rest of this, but just so you know, in case you're Googling some stuff and you see U, that's what it is. Also important to note is the units of this stuff. There is both the SI and the imperial versions of R. The R values that you see rated for construction materials in the United States is the lower one, which is feet squared hour per degrees Fahrenheit per BTU, which doesn't entirely jive with the SI because watts and BTUs are not equivalent. So that's why there's an hour in there. But in general, R is given as a function of either you're talking about the whole R value, which is basically everything other than the over inches, or you're talking about the R value per inch, right? So it should be specified typically. Foam insulation is usually given as R value per inch, but generally you might talk about a wall as having a particular R value. The good news is I'm going to do a lot of the math for you in this presentation, and so you don't have to worry too much about that. But you should be aware that there are two different units of R, and the numbers are completely different like any other unit, right? So if you get stuck in things that don't look right, that's one of the reasons why.
5 words you pronounce wrong 2 years before your brain starts shutting down. Dementia is now known as type.
YouTube. One last piece of conduction basics is that temperature gradient across a wall or an attic or a roof or a window is a function of the different R values and densities of R values as you go across. And so you can kind of see that there in my little ceiling, right? You have 5/8 of an inch of gyp wallboard. I think I have 5.5 inches, or I can't remember what I put, but something on the order of 5.5 inches of fiberglass batt, insulation, some OSB, and then maybe you stuck 2 inches of extruded polystyrene on the roof. And what you see is the temperature gradient will sort of, be steeper across things that conduct well. right? So the OSB has a kind of steep line because essentially the temperature on the inside of the OSB is going to be the same as the temperature on the outside of the OSB. And if you have better insulating materials like polyurethane or extruded polystyrene, which insulate better than per inch than things like fiberglass and cellulose, then you'll have flatter lines, right? And so this becomes important in not so much what we'll talk about today, except a little bit, but so some examples of this are, for example, you know, the windows in my old house. If we close the curtains, then we would get a lot of ice on the windows, right? And this is because there was this much air. You know, there was 4 or 5 inches of air between the heavy curtains and the window, but the windows had such a low R value that the temperature gradient through the air was actually flatter than through the window. Thus, the freezing line, the 32-degree line, which we call the isotherm, or it's really a plane, right? That freezing plane was inside the house, right? So that's why we got all that ice on the inside of the windows. And then there's condensation, other reasons for that. But so you get this all over your house, and if you live in Alaska, you've seen this a lot. But the important thing that I want to point out is the 32-degree line, right? And that 32-degree line is going to be straight across in this instance, but depending on what your house looks like, it may move up or down. You know, if you have an area of a lot of insulation, if you have an attic fan, that freezing line might move down because you're heating, you know, the area, or it might bump up and go, you know, like my example of the window is that the freezing line actually bumps down and goes into the house, right? So therefore the air inside the house, some of the air inside the house is freezing and then it'll bump back up. So you think of your house or your structure, it's got an envelope somewhere completely surrounding that envelope is a blanket that is the 32-degree line, right? So we're really concerned with that 32-degree line. And we have to think about both the insulation, but also the thing that I've glossed over, which is convection, right? So if you have leaks of air or hot air moving out of your house, then that's going to affect your lines. So, okay. Now, the last piece of concept here, I feel like I've said that times, is what is the insulation value of snow, right? Turns out that snow is a pretty good insulator. And so I went digging and found this fantastic article from 2011 on the thermal conductivity of snow. Now, if you look closely at this, the y-axis is in thermal conductivity. So that's the metric version of U in watts per meter Kelvin. And the density is in kilograms per meter cubed. And I know you can all easily translate that in your head to the densities that we use in this country. So I did that for you. And I converted it to R value per inch and density in pounds per cubic foot, right? And so, and this one in my head at least makes a lot more sense, because if you think about snow, when it's super light and fluffy, right, it's mostly air, and air is a pretty good insulator. It turns out that the R value per inch of air is in the neighborhood of about 3.5. And I didn't, so really this graph should probably, it doesn't go to infinity, right? It probably curves over and sort of heads towards 0 at about 3.5 to 4. But I didn't really bother with that because that's like this area down here, and there's not really any data, and we don't really care, right? So, but in general, it makes sense, because it should, when it gets to really light fluffy snow, which is about 5 pounds per cubic foot, it'll sort of probably curve over here. So, but more importantly, the other side of the graph, when we get to more dense air, snow, in the neighborhood of 15 to 20 pounds per cubic foot, it comes down here to about 1 and sort of levels off-ish. 2.5. So kind of remember those numbers, right? We have 2 is sort of medium fluffy snow. 15 to 20 is pretty dense-ish snow. The snow that we got in December, I believe we measured in the neighborhood of anywhere from about 6 to 10 pounds per cubic foot, right? It was pretty fluffy. when it first fell. So it was a lot of air. So it was probably way up here in this 2 to 3 Rs per inch range. And then of course, as it settles, right, and sinks and becomes less, one of the things that was sort of interesting to watch psychologically from the structural engineering community in both December and then the other big storm in January was people freaking out because their roofs looked like there was a ton of snow on them. And that was one of the reasons for that was because some of the snow densities were in the 6 to 10 pounds per cubic foot range, right? So we had 4 feet of snow on our roof, but it only weighed about 25 pounds per square foot, which is way below design for an anchorage roof. And so it wasn't really dangerous, but people looked at it and they were like, wow, there's a ton of snow. There's 4 feet of snow on my roof, right? And then 3 weeks later, we hadn't actually gotten any more snow, but it all settled down to the higher densities, and everyone was like, "Oh, we're good." And you're like, there's the same amount of snow on your roof, right? Anyway, so there's an element of psychology involved there, but so this is kind of a cool figure for that. And as we go forward, and
so maybe it is a good spot to mention that this year's snow, 2024, the snow we got in November was way up at like the 12 pounds cubic foot ish range, right? It's about the densest, heaviest, wettest, maybe 15. Really, really heavy and wet, right? And we got what, 20 inches, 2 feet, something like that. So there was, in November, we probably had, in the neighborhood of 20 pounds per square foot of snow. To start the winter, right? Yeah.
Scott, when you hear the weather report from the Weather Service, what do they consider an inch of snow? I've noticed that time and gravity tends to densify it
Yeah.
from first observation to subsequent. What do they?
So
consider?
I think, you mean us as engineers or
I'm talking about when the Weather
the
Service.
weather services? I think they mean when it falls. Because you hear, oh, we got 120 inches of snow this year, right? That's fallen snow. Like the day it falls, we measured 6 inches, and then 3 days later it's down to 5. So they mean the day it falls. So, and I don't remember if we talked about this later in the presentation, but the engineering community measures it in snow water equivalent. So, and there's a few stations around where they'll melt the snow as it falls, and they'll give you like, oh, we got an inch of water.
I've seen that with AWAS.
Yeah, it's all mostly, water stuff. So, and then actually, one of my colleagues over in computer science, who has a background in geography, has this great, I don't know if I show it in here, but he has this great plot of every year of the snow depth. And it's the snow on the ground depth. And so it goes up and then it goes down. And you're like, well, how did it go down in the middle of December, right? It's because it's settling. And then it goes up again and it goes down. So it never really gets more than like 36, 40 inches. It's basically the snow on the ground. That's a better.
Scott, I was just gonna mention that you have to take the number they give you with a grain of salt because not all snowfalls are of the same density. And so equating that into something engineering wise isn't very useful, I don't think, but it is useful if you're having to drive through it or somehow work in the snow to how much depth you have. But from a structural standpoint, when they say an inch of snow, doesn't really equate to a load particularly directly unless you know the density of it.
Yeah, and I should probably like plot storms on this, right? Have like November 23 up at 15, December of 22 not at 6. That would be you all. It doesn't matter when you're shoveling your driveway, right? It's heavy.
You can tell.
Yeah, we used to, as a kid, my dad used to call it heart attack snow. That dense and heavy, but stuff. But yeah, so and actually before people will ask, usually the newspaper will ask like, well, how much snow do we have? And nobody, it's kind of funny because this year they started, we'll go up there and measure, and we'll measure both the density and the depth and the weight. But this year they started asking before anyone had done any measurements. And so my answer was just based on like, well, we got this much snow, I figured based on shoveling, it's about this density, and so we probably have about this. So it's just always good to have a density in your head, so. Okay.
In years now, and I know some colleagues in town do some snow measuring. It'd be kind of fun to point, you know, to put some data points on here of like, you know, snowstorms we remember, right? Like the 2 ones in December, what range were they in here? Okay. So this is my attic example of what does that mean when you put some snow on your roof, right? And this goes back to, I didn't draw the line, but this goes back to this concept, right? As you have different insulating materials, then your temperature gradient changes and as you go through the attic. And so for the purposes of this, we're going to assume a completely sealed attic, right? This is not true, but we're going to assume a completely sealed attic. So there's a layer of air basically between your ceiling and your roof, right? Your insulation is above your ceiling, which is pretty typical in Anchorage. And so you've got your ceiling insulation, your air insulation. Your attic is actually a layer of insulation if it's completely still air. And then your snow, which is also insulation, right? Like we just talked about. So my first example, if it's cold outside, it's 0 degrees, and we have a 24-inch attic, then the bottom of the snow, which is what we care about here, is 20 degrees. So everybody's good, right? We have no melting of our snow. If you have a low slope roof and you're near the flatter parts, particularly near the eaves, and you only have 12 inches, and you have more snow, right? 36 inches at R2, so that's that sort of 10 pounds a cubic foot, which is completely reasonable for like December, what we got in December. Already the bottom of your snow is at 32 degrees, right? So, and it's cold, right? It's 0 degrees outside. So, so that right there shows you the differences between a higher sloped roof and a lower sloped roof and how much snow you get. If we keep with this example and we take the same 2 attics and we increase the temperature outside to 20, now your left attic, still with some fluffy 24 inches of fluffy snow, is now above freezing at the bottom, and the one on the right, same scenario, is at 42 degrees, right? So now your snow is heavily melted, right? And so here's an example of what is unfortunately somewhat common in Anchorage, which is probably like a cathedral ceiling, or some other construction where there's a very small airspace, only 4 inches of airspace. And here we have the same set of scenarios, 20 degrees, 24 inches of snow. And now we're at 41 degrees at the bottom of the snow. And the same scenario, except for 36, we're at 45 degrees, right? So reducing that airspace, even again, this is a sealed airspace, right? No air movement at all. Just reducing the airspace gives you much warmer snow. And then so what's going to happen? Well, it's going to melt, right? The bottom of your snow, there's going to be a temperature gradient across your snow. So the bottom of your snow is going to start to melt. If you have a sloped roof, that means it's going to, the water's going to go somewhere, right? We'll talk about that in a little bit, but it's going to melt. The snow is going to densify, and then you're going to end up with this, right? So the snow is going to densify. I lowered the R value because the snow densifies. I reduced the amount of snow. Basically, I reduced the amount of snow and changed the R value until I got to 32 degrees, right? So this is sort of what happens, right? And it is that, you know, you're going to get water. Things are going to melt and condense and densify, and until you get to a point where it freezes again. Right, and so that might be, depending on the R values and stuff, that might be, 14 inches of snow. Over here, when it's 0 outside, it's 30 inches of snow, right? So the outdoor temperature has an effect on that as well. Here is a poorly insulated house with people that like it to be hot. So I increased the indoor temperature to 78 degrees from 68 degrees, which I've totally seen and is wild. But my parents, who don't live in Alaska, that's about right. So if you have a poorly insulated house and you increase your temperature, then even with 48 inches of snow and a nice big attic, you still have 32 degrees on the bottom side, right? And if you increase your outside temperature, you've got a lot of melting, right? And so that's probably enough of those. All right, so lots of other factors that I haven't talked about, right? We have chimneys that are poking through this attic space that are adding heat. We have bathroom fans and plumbing vents. We have envelope penetrations themselves, right? You're not going to get a perfect fit around your bathroom fan, right? So you're going to actually get convection through all those utilities, in addition to reduced amount of insulation over the attic fan or the bathroom fan, et cetera, et cetera, et cetera, right? So I didn't mention stepped roofs, right? If you have a whole bunch of walls that are going up and down as your roofs go around, then you've got heat coming from the wall potentially. Very complicated system. But the basics of, how much heat do I have, how much cold do I have, and how much insulation do I have? That's kind of the basics. All right, and then oftentimes many people have heard the terms cold roof and hot roof, and so here's the formal definition. The cold roof stays at the ambient temperature, and so the idea here is everything I just talked about in terms of conduction occurs, right, no matter how much insulation you put, but I didn't give you an R60 or an R80 roof, which exist, right, but basically the same stuff happens, it just happens slower, right, you're still going to have heat going through no matter how much insulation you put on. And so you have to get rid of that heat, and with a cold roof, you use convection to get rid of that heat, right, so you have to have a positive flow of air, which Bart will talk a little more about, but you have to have a positive flow of air to remove that heat in some shape, some way, right? And then you have a cold roof because then your snow stays frozen and you don't end up with that water problem. Here are some designs of, sort of normal, and again, we're implementing the stack effect here, right? We have heat and cold above, and so the air will naturally kind of get sucked through as long as you don't go and blow a bunch of insulation into this spot, right? Or if your roof vent, if you don't have E-vents and your roof vents are completely plugged with snow, then you have a problem, right? So you can foresee a bunch of stuff that will not go right. Here's an example of some cold roofs that work. These are Bart's photos, actually. And he'll talk more about the eaves melting first and why that happens, but that's an indication of cold roofs. And then the opposite of that, of course, is the hot roof, right? The idea is that you have no insulation and no convection, right? You have hopefully you have insulation, right? You might have no insulation, right? Yeah, that would be a very hot roof, right? And so basically you get what I described before, which is heat. The bottom of the snow is over 32 degrees, and so then you get melting, and your isotherm line or surface is up inside the snow, right? It's basically, if you go back and look, I didn't mention that, but in this previous one, it's not that one. Oh. What are you doing? There we go. This one, this black line here is the isotherm, right? That's the 32 degree line. So you have to, often you have to think about your details, where your wall meets your roof or things like that, which is a whole other presentation. But in this case, that line moves up above. And what you'll notice, of course, is that the water flows down until it hits that line and then it freezes, right? And so you've got this classic ice damming effect where the eave is cold, and then the line here crosses through that ice, and then you have a little lake of water up here. And the interesting thing about this is that the water stays water, right? Because this isotherm is a constant thing. Of course, this is a dynamic system. you might get water streaming across the top, you might get, changes in temperature outside, you get more melting of snow, but the water's there, like it's not going anywhere, right? And so, and I think on the next slide, we talk a little bit about, well, this is what I just said, right? And this is a picture, is this your house?
This is my house.
This is Bart's house,
I built it.
prefix, where the water actually leaked down. This is a cool picture, right? Because the water actually leaked down the wall and froze because big, huge icicles. The ice damming is happening and the roof is failing and allowing that water to leak through that location. And so
More on that later.
yeah. So that's what's happening. And so one of the things some people say, well, is a hot roof bad? Well, maybe not, right? And so you can decide to have a hot roof. I didn't take a picture of it. I saw a hot roof. It was actually out in the valley about a couple of weeks ago, and it didn't have any icicles on it. And it was because it had the insulation went all the way to the tip of the eaves, and the eaves were really short. They were only about 4 or 5 inches maybe. And so the water was and there was only about 3 inches of snow on it. And this is like February, so maybe 6, but the snow was melting, right? Like there was only this much snow on the roof. But there was no icicles because the eave was so short and the heat from the building was kind of migrating through the foam. It was a foam roof out to the end, and so there was no ice. So if you're careful and that's what you want, then you can make a hot roof and it'd be okay. These are the problems, right? You need to have, you might get ice, you might get cool icicles, right? But you need to make sure your eaves can support that load. You need to make sure that pool of water isn't going to get into your OSB or your roofing material. You need ice shield, basically a waterproof roof up a certain height, etc. So you just need to know it's a hot roof. Here's some great examples of hot roofs. It's kind of fun once you understand all this. You can kind of walk around town and just look at them. Bart's going to show you a bunch of examples of hot roofs versus cold roofs. Here's an example of a hot roof or a cold roof that isn't, right? So you can see in the yellow circle there, there's supposed to be a vent, but it's not doing its job, right? Either the slope is too low, or the eave vents are plugged, or there isn't a big enough height difference between the two to get a good stack effect, or whatever. It's not working, right? And it's very obvious that it's not working. So I think I already kind of hit most of these, right? We understand that more depth and higher insulated snow is gonna cause your freezing line to move upward. Cold temperatures, in some ways the cold temperatures actually help because it keeps the snow cold, but in other ways it causes the ice damming itself to be worse, right? Because once that water is moving, as soon as it comes out, either what we call daylights, it's going to freeze, right? And so some that's happened a bit this winter, and you've seen more and less flow because of the temperatures. The other thing that I didn't actually put in here, so this is my, I already said most of this, right? Is it, if you're going to have a hot roof, then make sure you design for it essentially. I want to leave enough time for Bart to talk, but the other thing I was going to say, actually, let me back up for a second. So one of the reasons that we've had such a problem with this winter, I alluded to it. This is my own speculation. Is I alluded to the snow part, right? We had a lot of snow. It was very insulative, and not only does the snow add to the insulation, it also adds to the volume, right? Because once you get melting under the bottom, there's just a ton of water coming off. The other thing that happened, which I haven't heard too many other people talk about. I want to go back to my old roof.
And we're back in third quarter planning. Adams is quarterbacking this project, and she is looking.
Or actually, no, I'll go back to ice dam. is that we had a period in the end of January where the temperature got up to 42 degrees for a couple of days. And then after the 2 days of 42 degrees, it actually sat at about 29 degrees for about a week. And so what happens with a cold roof is that if your attic is at 42 degrees, you're not going to get a lot of, you're going to get melting, right? Your cold roof becomes a hot roof when your attic is at 42 degrees, right? And so irregardless of how much insulation and convection you have, right? In fact, in this case, your convection is actually hurting you, right? Because you're sucking in the warm air that's outside. And if you live in a super shady spot where you don't, or a low, you live by Campbell Creek Science Center, which is always colder than the rest of town, and your house is colder, then maybe you're okay, right? So that happened, and all the roofs warmed up, and then it didn't cool down. It didn't cool down very fast. It stayed at about 30 degrees for a week, and so melting continued. Some of those attics probably held that 42 degrees, and so that's one of the reasons why people who have never. That's what my speculation of one of the reasons why people who have never seen ice damming on their houses before saw ice damming. Right? We had all this snow, and then we had this warm up. So that's kind of potentially what happened. Okay, I want to skip that and turn it over to Mark.
How would you say, was that similar to this year too? Seemed like.
Yeah, I got a call from.
So, yeah, it's interesting that we haven't seen more ice damming this year. Because of, the last 2 weeks we had some warm temperatures, and so I expected there to be more ice damming, like similar to last year, but we haven't seen it quite as much as last year. So, and maybe it's because it didn't sit at 29 degrees per week, right? It was warm and then it was cold. I think so. I don't know. Maybe Bart has thoughts on that, but
I haven't been out and about a whole lot, but the just looking at my own roof, the only icicles I get are in the spring when it starts to melt and it freezes at night, and then they fall off the next morning and that sort of thing. Well, with that big warm up that we had this year, it melted quite a bit, and it did, but as soon as it got cold, it was still melting. So I have actually a series of icicles all down my roof, which I don't normally get because my roof is definitely a cold roof. But I have a little tiny ice dam on the edge of my eaves that I haven't had before. So it's interesting.
oh, it's old. And the other thing that I've seen in my neighborhood is that there's been a huge variation in amount of snow and snow cover, depending on where exactly your house is and how it's facing, right? Because there's houses that with big wind exposure that are almost bare, or people shovel them and then they melted during the big melt, and then other houses that were in the shade and they still have tons of snow on them, right? And these are houses that are across the street from each other. So, so I think we've seen a huge amount of variation this year. So, whereas last year it seemed like everyone had an ice.
Scott on Wednesday saying, "Oh, I'm giving this presentation. Have you heard about it?" And I said, "Yeah." He says, "I'm using your slides. You want to come help with it?" So here we are. And he's done a great job of explaining a lot of things. And I'm going to just tell stories, probably. So, how do you work? So, with dams, you can live with it, and that's an option. You can attack the symptom and deal with it that way, or you can turn the roof into a cold roof, which is a long-term solution right up there with live with it. But sometimes it's really the only affordable solution is to just figure out how to deal with it. So the way you deal with it is you make sure that your roof membrane is such that when you build the ice dams, the water doesn't get up under the shingles and into the house. And you make sure that your eaves are strong enough to hold the snow, though I've never had a problem yet where I've seen where the eaves haven't been strong enough to hold the ice. Usually they have plenty of capacity structurally, so that's not a problem. One of the problems that may exist is how do you keep the ice from falling on people and things you don't want it to? And usually that's a roof configuration problem more than anything else. One of the pictures that we had back here was my mom's house, and the entryway used to get ice. You can see icicles off on one side of the roof there. Would fall. You'd have to walk underneath all that, and the ice would get it. So when doing some remodeling, we changed the roof structure to re-divert the water so it doesn't go over where people go in and out of the house. And yeah, also that ice used to build up on the walkway, and it was a real hazard. So there are some things that you can do architecturally to kind of change that problem. So a lot of people are asking right now, what can I do? I've had all these problems this winter. What can I do to prevent it in the future? So we'll kind of talk a little bit about these things. And if you're going to change it, then there are some requirements. First of all, there is a structural requirement to make sure that if you have icing in your area that they actually double the snow load over the eaves, and you design to make sure that the eaves can handle that. And you can, retrofitting that might be kind of tough, but you can do that. Let's attack the symptom here a little bit. I've had a lot of phone calls this winter about roofs and problems that people are having right now and how to deal with it, because it's raining inside their houses and all these fun things are happening, which had never happened before in the 40 years or whatever that they've lived in their house. There are some things you can do to try and take care of the ice dams. You can follow them with heat tape, and you see this occasionally as you drive around town, all the zigzags of the heat tape on there. And that will create paths through your ice dams so that the water go through. You have to be careful a little bit about that. One thing that I recommend with people, it's kind of late to add that in the middle of the problem. The other thing I didn't put in here is suggest that you just get rid of the water source. So that's shovel your roof. And you don't just shovel it at the dam. You have to shovel all the way up the roof, because that's your water source that's going to be coming down the hill. One thing people see if they shovel partway up the roof is their cold roofs now are cold right up to there, and they create new ice dams right where they had shoveled to. So you need to get rid of all the water uphill. So you'll never have an ice damming problem if you don't have snow on your roof. All right. So if you
also don't shovel your roof onto another part of your roof.
Oh yeah.
There was some instances of that, and you can cause your roof to collapse.
Yeah.
Shovel it off.
Shovel it off. There's some strategies, and most of them involve people who are younger and fitter than I am to make sure that they get done. But we've had friends fall off roofs and all sorts of fun things. And so our son, the ER doc, gets to see those. But anyways, to deal with the symptom, you need to either thaw the ice dams or get rid of the water source. And that's really your solutions at this particular time when things are building up. Hot roofs are really nice because they do snow removal for you, right? They melt it all and it all goes down to where it refreezes. But so you probably don't have as much to shovel as if somebody has a cold roof. The other thing, making a roof a cold roof is kind of a long-term solution. You're probably not going to do it in the middle of the problem. You're going to do it in the summertime or sometime when it's easier to do that. And if you remember Scott's slides, the best thing you can do is remove the heat somewhere between the insulation and the bottom of the roof surface. So convection is generally the way we're going to do that. We need to pull the air out of there. There's a number of strategies that you can do to do that. Another problem, seal the vapor barrier. It's actually more of a problem with spring thaw. If you have bad vapor barrier, you get ice inside the roof and it comes down in the spring, so oftentimes through light fixtures and other places. If you look at his mathematical models, increasing the insulation will also make it so you have less heat to pull out of the roof system, but it won't eliminate it. But the biggest thing you want to do is increase the ventilation, and you need to do that correctly. So let's talk about this story. So I'm real proud of my house. I started building it in 1983, and we're still building it out in Tuyaki River. But I had never had a real icicle on my house ever, right? So when I went to re-roof it a number of years ago, I didn't even bother with ice shield. I said, why? I got 30 years of experience with no ice damming, so I don't need it. So, and we have no building oversight in Eagle River, so I can do whatever I want. And so I did that. Well, the other thing we did is we had a one-story garage, and the heat pipe that came out of the garage was up in the roof far away from the edge. Well, we raised the roof, inserted a second floor, moved the heat outlet right up against the wall, and thought everything was really nice until that winter, and I noticed all these icicles forming, realizing that while I had a really nice cold roof in this one location, I had a whole lot of heat. And so how do we deal with that? Well, we could get rid of the snow. In this case, I don't need to shovel the whole roof, just over the influence of the heat source. And but it was really cool from a professor standpoint. Yeah, here we go. If you look here, the edge of the ice followed this curve right here of the isocline, and I had a nice pool of water right there. And it was, the bottom of that ice was curved just like I expected it to be in the picture right there, which is really, I was excited about that. But we ended up shoveling, and next summer decided to go in and deal with the problem. And one way we decided to deal with in this case was to build a very ventilated chimney box around it to take the heat from that pipe out as soon as possible. We also cut great big holes in the roof underneath that, so all the heat from the roof space goes up and through. Probably shouldn't have put the vent in the bottom because I have plenty of E-vents and everything's going there. But as you can see from the picture on the left, you see a little bit of ice damming in there. You're going to get some of that on almost every roof, just because when it warms up to 42 degrees and you get all these things that are happening, you get a little bit of ice sometimes on the end of the eave, but it's nothing like the dam that was there before. And this has been functioning real well for about 15 years, and so I'm pretty happy with it.
Call your doorbell camera company and cancel the subscription. This brand new subscription-free mini one.
All right, this picture didn't turn out very well, but you know, add ventilated space. So I'll just go to this picture. So this is actually to solve the opposite problem, which is heat. There's a little house that we have in Arizona, and had a lot of problems with heat, and other things needed to be re-roofed. I tried to hire a roofer to do what I'm doing here, and they say we don't do it like that in Arizona. That's fine, so I just did it myself. But what I ended up doing in this case, put a metal roof on, and I didn't have to put a new diaphragm down. I just raised up and put some stringers across the roof to put the metal roof on, and a ton of holes were placed on the eaves down here, and a ridge vent on the top. And then the building official came by and wanted me to put holes all over the roof, so I did that too to get heat out of the attic space. And it reduced the heat in the house empirically from 15 to 20 degrees over what it was in the summertime. And of course, they don't do it like that in Arizona, but you can do this in Alaska for the same reason, that is to pull the heat out of the attic space and vent it somewhere else. You know, we talked about having that space in there, and I've got a friend of mine with a real icing problem. I've been trying to get him to do this for years, and so far I haven't convinced him. But so anyways, the idea is you can go back and add ventilated space, even if you have a cathedral ceiling, you've got some other things going on. You just basically build a roof over a roof. And this is actually, the building official wanted me to show that the added weight of this new roof was gonna help out, and I kind of laughed at him because we took 2 layers of shingles off of that roof and replaced it with a metal roof, which was infinitely lighter, and so we got past that one pretty quick. But it works. So the idea is you want to increase the ventilation, and also some of these roofs that are kind of flat, you end up with not a lot of vertical space between where the air comes in and where it goes out. And so you can add chimney type cupola things on your roof that will increase that height and increase the airflow that you go through there. So I had a friend of mine in Eagle River back in the 80s who was complaining about his old house that always had all this ice and a very little slope to it. I suggested he do something like this, and he went off and thought about it. And next winter he comes to me and says, it really worked. And I said, oh, you did it? And he goes, yeah, I put 6 of those things on my little house. So, you know, you get enough of them, you know, it'll ventilate, and it works really great. But the part of the idea here is to increase the airflow through the system. And if you can increase the height between where the air comes in and where it goes out, you're going to increase that airflow, and it's going to take more heat out as you go. So I just went on the net and looked for things, and these are from hot climate areas, but roof vents are not a new thing. They use them to remove heat everywhere. I mean, even old barns used to put these cupolas on the top of them just to keep them cool inside. And it's the same idea. You could build one of those on a house in Eagle River. It looks really cool. I don't know how the Anchorage guys like it, but there you go. Eagle River's just that kind of place. So hot roof, cold roof is all about design. These 2 pictures were taken about a minute apart on neighboring houses. One's hot roof, one's cold roof. Same environment, same exposure, same everything. But you can do that. You can tell hot roofs in particular because you'll notice it's thawing over the house, over the garage in this case, and you can see every single truss, which has a little bit more insulation than OSB. And the snow doesn't melt over the eaves; it just melts over the hot part. What you'll find in cold roofs is that the melting, when it does take place, is actually going to happen over the eaves first and over the house second. So you're going to see these things happen. These were taken just last month, just wandering around town. Hot roofs are particularly hard on rain gutters, which are, I'm never really a fan of rain gutters up here because of this particular problem. See the rain gutter? This is up in Government Hill. So after Scott called me on Wednesday, I says, you know, I'm retired. I got a lot of time on my hands. So I took my drone. I do photography as my retirement hobby. And somebody talked me into a drone lately. I just flew it around my neighborhood, just looking at everybody's roofs. So this is a waiver. No, I actually looked at that. The airspace over your house is not your space. I can fly my drone wherever I want. And this time of year, everybody's inside, so they don't know. So this is my neighbor across the street. She has an unheated garage in the front of the house. And we were there when they built it. I don't know how to write this. Here we go. Nope. There we go. This pointer is lousy. Anyway, so this is the cold roof. And you'll notice we've had some warming and stuff over the last week or so. And so it's melting around the eaves. It's really great. She had huge icicles in front of her door. She lives on the left side. And she might not have shoveled a lot of this, but her tenant on the other side didn't shovel anything. And you talked about infrared to see where the heat loss is. You don't have to worry about infrared up here to figure out where your heat loss is. You just get your drone up and you look down on the roof, and you can see what the problems are. And so obviously she doesn't spend a lot of time, I guess, upstairs and probably keeps it cool, but her tenant does, and it keeps it really. And they've lost a lot of snow here. And all that snow has come down and frozen the ice dams all over the edges of this, and same with the other things there. So there's a place where we're having heat loss, and the heat, it makes sense because most of the heat's gonna be higher in the attic space, and so that's where it's gonna start. The other thing you'll notice on the eaves, there's still snow on the eaves, all right, because that's cold and it's not melting. So we've got the eaves with some snow going on.
Drinking coffee every day didn't work for me, but I couldn't figure out why until I went from 180.
So here's another neighbor's house. Great cold roof, but he talked about roof penetrations are evil. All right, they cause a lot of heat. We're going to talk about this. And you can see where the roof penetrations are. And this year, it's a particular problem. Most of the time, all you're melting is the snow right around this. And so there's not a lot of water finding its way down. You get some, and you get some damming and stuff around here. And same with over here. But we've had so much snow that I'm going to show you a kind of dam that I never expected to see. But you can see in their warm roof or cold roof that there are some hot spots where the utilities come through. Ridge vents. Everybody always asks me about ridge vents. Don't they get covered with snow and don't they have problems? And I guess they do, but as near as I can tell, they're the first things to melt. And there's not a lot of snow around them. So that snow probably, as that water goes down, it freezes long before it gets to the eaves. So I imagine that there's a little bit of ice underneath the snow there. So if you're up on your roof shoveling, be aware of that. It could be kind of hazardous. But once they open up, they do quite well. These houses have great southern exposure. And so what we see around the eaves of these houses is some melting going on over the eaves already now that spring is starting to spring on us here. And so the roofs these houses don't have particular icing problems, but they do have places where heat is escaping from the houses. All right, this is an older home in the neighborhood, and they have a few apartments in and around it. In the Arctic Engineering course, which some of these slides came from that I did quite a long time ago, we show this house on the left, a really steep roof. It has slab avalanches every year, which is really cool, right over the entryway. So they've built a little roof over the entryway to keep from getting hurt. And you can tell where the unheated carport is. And in the two apartment buildings, a lot of heat going on, and the snow and ice are still building up on the eaves. But this one has kind of extreme hot roof situation going on. Here's a mix. They have a heated garage. See, there's a heat thing over there, but they probably don't keep it really all that hot, and may be well vented. But the older part of the house is definitely a hot roof, and then the newer part of the house has a cold roof, so you can have some of the same in both. And the reason why I kicked this picture in, they added on to it a couple of times, but you can actually see the ice shield that they put on the roof. They covered the whole roof with the ice shield, all right? And that's great. You're not gonna have any icing or any water leak problems if you make a membrane like that over your entire roof. It's kind of expensive, but it's an option. I threw this one in because if you look real close on the ridge, they don't have a ridge vent, but they put in a whole bunch of little vents all around in here. Those are not all utility vents. Some of these are. Some of these are bathroom vents and that sort of thing. But they've just put those up there instead of a ridge vent. And sure, you can see there's some melting along the ridge, which is fine. They don't have icicles. So actually they got a little sheen of ice underneath their snow. But that's another way, you can add something to your roof that will do that kind of thing. So this is my roof. I was smug online with my friends who were talking about all the water problems they're having. I says, I haven't had water problems in the 38 years we've been in the house. And I built it myself. I'm a wonderful guy. And then Sandy calls me into the laundry room and says, what's all this water falling down the wall? And I says, I went outside. I didn't see any icicles. I said, I saw a little bit of an ice dam, but nothing that would do that. And I'm thinking, how in the world did that happen? So I had to my words a little bit. So I went up on the roof and I noticed around all this is a bathroom fan, this is a bathroom fan, this is a kitchen fan. And there's a lot of snow around each one that has melted, and all that water had to go somewhere. That's a cold roof. Where does it go? It goes just down from the vents, and it freezes and creates ice dams a long ways away from the eaves. And so I had this problem with ice dams occurring where I never thought I would ever see them. And I think a lot of it has to do with the duration of the long snow that we have here. And that's all ice on my roof that came from those vents up there. My solution to that was to shovel to where the snow was no longer melting. And I'm getting old, I didn't want to shovel my whole roof. So I just went to where it was there. And the rain stopped in the laundry room, which is a great thing. So we'll be reevaluating this. Possible solution, don't use these little rooftop vents, use something that pops up a little higher, gets above the snow, and maybe it won't melt all that, and insulate it too, because you can see the plumbing vent has also melted some snow around it, but not nearly as much as the fans did. So I don't know, maybe I have another summer project going on here.
There's one simple vision hack anyone can use to improve vision, so you can say goodbye to your optometrist for good.
Hey.
Okay, Bart, did you fix it last summer?
No, I just went out and shoveled again this year preemptively.
Okay. Well, we're gonna run out of time. We've already run out of time, so that's probably a good place to stop. Feel like we just kind of took a lot of questions after that. I think I skipped this whole part. So, I guess I'll give the 2-minute update on this year. I know there's been a lot of questions about collapsing roofs, right? So hopefully, especially the engineering community has heard enough and gotten their heads around the problem to know that you don't really have to worry about it if it's your house for the most part. But the Muni has sent out letters to about 1,000 buildings, mostly flat roof, pre-1990. Supposed to be wood truss roofs, but they don't actually always know. So sometimes you get one that's not. So basically said shovel. And that has nothing really to do with the snow, except that the snow weighs something. It really had more to do with the fact that those roofs are effectively defective. So anyway, we can answer questions about that. We've been doing some testing on some of the metal plates and talking to the Muni and talking to SEAC, and there's a whole world of issue there that has to do with the history of those types of buildings. And the only real relevance to snow loading is that we have a giant amount of snow, right? Unfortunately, with the melting and the wind, we have much less snow now. Most of the buildings, it's actually really good. We've had 6 collapses, right, this year, 6 or 7, and nobody has had any serious injuries, a couple close calls. Last year we had 17 collapses, so and we actually have more snow, more weight this year than we had last year, so that's a good thing. It's a good story. So anyway,
But it looks like you may have something to add. Yeah, go ahead.
Yeah, I was gonna say, I was designing buildings in Anchorage in the early 80s. And so I've been keeping an eye on all the ones I did that have those flat cord trusses. So fortunately, none of them have come down yet, but it was a real common thing, and that's just the way we did the warehouses and larger span roof systems in the day. So yeah, I'm curious on the research on the connections. So
yeah, and I have some reports from the structural engineers in town where they've gone up and done some checking, and the plates they've found buildings where the plates are starting to peel away, which is kind of what happens. So there are some roofs that were in sort of active state of failure that didn't collapse, and they didn't make the news, but because they got shoveled. But there was a whole slew of buildings that were having issues that you hear about, and some that weren't, right? Plenty of buildings that are fine stuff. So yeah, so And before I forget, the password for today is structure.
Structures with an S.
Structures with an S.
Yeah, it's all lowercase.
Yes, all lowercase. For those of you that need your PDHs. Is that in our title? It is in the title. All right. Does anyone have any questions? You already asked them.
Okay, thank you very much.